China just built a working computer processor out of a material that is only 3 atoms thick. Not 3 nanometers, 3 atoms. If you lined up 300,000 of these layers, you would still be thinner than a human hair. And somehow, inside a research lab in Shanghai, this material just ran real software instructions. That should sound impossible, almost like science fiction dressed up as a lab result. For 70 years, every computer on Earth has run on silicon. Your phone, your laptop, the servers behind every AI model you have ever used, all silicon. So when a university team says they built a working processor without it, that claim deserves real scrutiny. This time, the scrutiny holds up. The research was published in the journal Nature in April 2025, one of the most rigorously reviewed scientific journals on the planet. This is not a press release. This is peer-reviewed physics. Today, we are breaking down exactly what Fudan University built, what is real, what is exaggerated online, and why this tiny, slow laboratory chip might matter more than its specs suggest. Let's start with why this research even needed to happen. For decades, the entire computing industry has followed one simple playbook: shrink the transistor, fit more of them onto a single chip, use the extra transistors for more performance, lower power draw, and new features. This is the strategy behind Moore's law, the famous observation that the number of transistors on a chip tends to double roughly every 2 years. It is the reason a phone in your pocket today has more computing power than a room-sized supercomputer from the 1980s. But silicon has a physical ceiling. As engineers shrink transistor channels down toward just a few nanometers, the material starts fighting back. Electrons no longer stay where they are told to stay. Current leaks through the transistor even when it is supposed to be switched off. Heat becomes harder to remove. The clean, predictable on-off behavior that digital logic depends on starts to blur. Chipmakers have fought this with clever engineering. FinFET transistors and gate-all-around designs wrap the control gate around more of the channel, restoring some control. Taiwan semiconductor manufacturing companies Samsung and Intel are all racing to build these next-generation transistor architectures at 2 nanometer and even angstrom-class dimensions. But every new generation gets more expensive, more complex, and closer to the physical limits of what a crystal of silicon atoms can actually do. That is the backdrop against which researchers everywhere are hunting for a plan B. Some are exploring new transistor geometries, some are stacking chips vertically, and some, like the team at Fudan University, are asking a more radical question. What if the problem is silicon itself? It also helps to understand just how expensive the current path has become. Building a leading-edge silicon fabrication plant today costs somewhere in the range of $20 to $40 billion, and the extreme ultraviolet lithography machines needed to pattern the smallest features, made almost exclusively by the Dutch company ASML, cost well over $150 million each. Every new node shrink demands more of these machines, more precision, and more capital. That economic reality is part of why so many research groups, not just in China, but in the United States, Europe, and South Korea, are pouring money into alternative materials research. If silicon scaling keeps getting more expensive for smaller performance gains, then any material that offers a genuinely different path forward becomes strategically valuable, even while it remains decades away from commercial competitiveness. Technology explained. So what exactly did they build? The processor is called RV32WGI. The name comes from 2 parts. RV32 refers to the 32-bit RISC-V instruction set architecture it runs. WGI is a term borrowed from Chinese philosophy, roughly meaning limitless or without boundary, a fitting name for a chip trying to push past silicon's boundaries. The processor was built using molybdenum disulfide, a compound written chemically as MoS2, made from 1 layer of molybdenum atoms sandwiched between 2 layers of sulfur atoms. That gives it a total thickness of about 3 atomic planes, which is where the 3 atoms thick headline comes from. It is worth being precise here. Molybdenum disulfide is not perfectly flat like graphene. Its atoms bond at a slight angle, giving this material a subtle zigzag structure, but functionally it behaves as an extremely thin 2-dimensional semiconductor. And that distinction between semiconductor and conductor is the whole reason this material was chosen over graphene in the first place. Graphene is famous, strong, and highly conductive, but it lacks a natural band gap. Without a band gap, a transistor cannot fully switch off, which makes graphene a poor foundation for digital logic that depends on clean ones and zeros. Molybdenum disulfide, by contrast, has a real band gap. It can be pushed into an on state and pulled into an off state with much cleaner separation, which is exactly what a logic circuit needs. It is also worth noting that molybdenum disulfide is not the only 2-dimensional semiconductor candidate under investigation. Researchers around the world are also studying tungsten diselenide, black phosphorus, and various other transition metal dichalcogenites, each with slightly different band gaps, mobility characteristics, and manufacturing challenges. What made molybdenum disulfide a practical starting point for this project is that other groups had already demonstrated wafer-scale growth of the material on sapphire substrates in prior published work, giving the Fudan team a manufacturing foundation to build on rather than starting completely from scratch. The finished RV32WUGI chip contains 5,900 transistors. Corrected, original stated 5,931. The Nature paper and most technical sources cite 5,900. IEEE Spectrum's coverage cites 5,931, likely a difference in whether test structures are counted, packed onto a single die measuring 6 millimeters by 6 millimeters. Either way, this is not a single transistor demonstration. This is thousands of working devices wired together into a functioning system. The chips were fabricated on 4-inch sapphire wafers, with 24 individual WUJI dies produced per wafer. Sapphire was chosen because it is an excellent electrical insulator, keeping each transistor isolated from its neighbors, similar in spirit to the silicon-on-insulator technique already used in advanced commercial chips. To be clear about scale, this processor is enormous compared to a modern silicon chip. Its transistor channels measure roughly 3 micrometers, thousands of times larger than the sub-2 nanometer features found in a cutting-edge smartphone processor. A single modern silicon chip, the same physical size as RV32WJI, could theoretically hold not thousands, but potentially billions of transistors. That comparison matters because it tells you clearly what kind of milestone this actually is. It is not a milestone in density, it is a milestone in reliability and integration. Think of it less like a sports car and more like the very first working engine ever bolted together. Nobody expected that first engine to win a race. What mattered was that every piston, valve, and gear worked together in sequence, proving the underlying concept could run as a complete system rather than as isolated parts on a workbench. Here is the technical wrinkle that made this project genuinely difficult. In a normal silicon transistor, engineers control its threshold voltage, meaning how much electrical push is needed to switch it on, by doping the silicon with impurity atoms. That trick does not work with a material that is only a few atoms thick. There's no room to implant dopants without destroying the structure. So the Fudan team had to solve this a different way. All the transistors in RV32WUGI are naturally N-type, meaning they conduct in only one direction of behavior by default. Instead of doping, the researchers used 2 different metals, aluminum and gold, to wire the transistors, and they discovered that the choice of metal and the surrounding materials could shift each transistor's threshold voltage in a controlled, repeatable way. From there, they built depletion mode inverters, the fundamental building block that flips a 1 into a 0 and a 0 into a 1. That single innovation is what allowed the rest of the chip to exist, because without it, there would be no reliable way to build digital logic gates out of this material at all. From that foundation, the team constructed a standard cell library, 25 different types of logic building blocks made from these 2-dimensional transistors. Chip designers rarely draw every transistor by hand. Instead, they assemble processors out of standardized pre-verified logic cells, the same approach used across the entire silicon industry. Fudan's team built AND gates, OR gates, inverters, registers, and more complex compound units with names like OAI-21 and AOI-22, all made from molybdenum disulfide transistors instead of silicon ones. These cells were then combined into a full RISC-V 32-bit processor core, organized around 9 functional modules, handling instruction decoding, data movement, and arithmetic. To prove the processor actually worked, the team demonstrated it executing real 32-bit addition, adding 2 full-width binary numbers and producing the correct result through the chip's arithmetic logic, its registers, and its control circuitry. That might sound like a small party trick, but it requires the entire processor pipeline to function correctly in sequence. Instructions have to be fetched, decoded, executed, and the results have to be stored, all without a single transistor failure breaking the chain. Manufacturing consistency was the real breakthrough here, more than the material itself. Previous attempts at 2-dimensional integrated circuits had topped out at around 156 transistors, according to the research team, because wafer-scale 2-dimensional films are notoriously inconsistent. The film can grow unevenly across the wafer. Metal contacts between the semiconductor and the wiring can vary from device to device. Microscopic defects and threshold voltage drift can accumulate across thousands of transistors until a chip simply stops functioning. To fight this, the Fudan researchers used machine learning to analyze how each step of the fabrication process affected transistor performance, then adjusted both their manufacturing recipe and their circuit design together, rather than treating them as separate problems. The published results are genuinely impressive. Individual transistor yield came in around 99.9%, with chip-level functional yield around 99.8%. Corrected. Original stated approximately 99.77%. Verified published figures cite roughly 99.9% overall and 99.8% chip-level over yield. That said, the team was honest about where the process still struggles. Smaller test structures like 8-bit registers only reached about 71% yield, and larger 64-bit registers dropped to roughly 7%. Bigger, more complex structures are still far harder to manufacture reliably, which tells you exactly where the next years of research need to focus. Now let's talk about performance, because this is where online headlines tend to get carried away. RV32 WUJI runs at approximately 1 kHz. A modern smartphone or laptop processor runs at several billion cycles per second. That is not a small gap. It is a difference of roughly 6 orders of magnitude. During arithmetic operations, the chip consumed about 0.43 milliwatts of power, an efficient number, but one that reflects how little computation the chip is actually doing, not some breakthrough in power efficiency at scale. The researchers themselves, including corresponding author Peng Zhou, have been upfront that this prototype cannot and will not compete with an Intel, AMD, Apple, or Qualcomm processor. It was never designed to. The honest comparison is not against a modern smartphone chip. It is against the previous state-of-the-art in two-dimensional integrated circuits, which topped out in the low hundreds of transistors. Against that baseline, RV32WJI represents a genuine leap from isolated laboratory curiosities towards something resembling a real systemic engineering platform. Industry impact. So why does any of this matter for the broader chip industry? The most direct answer is heterogeneous integration. Modern chip making is already moving toward stacking components vertically, high bandwidth memory stacked in layers, chiplets combined inside advanced packages, and logic dies bonded on top of other logic dies. The problem with stacking more silicon layers is heat. Traditional silicon fabrication involves process steps hot enough to damage circuitry that has already been built underneath. Two-dimensional materials like molybdenum disulfide can potentially be grown or transferred at lower temperatures, which opens the door to adding thin functional layers on top of finished silicon chips without frying what is already there. In that scenario, silicon would keep doing what it does best, handling high-performance computing cores, while a thin 2D layer above it might handle sensing, low-power auxiliary logic, or specialized functions. This is not a silicon replacement story. It is a silicon complement story, at least for the foreseeable future. This kind of vertical thinking is already reshaping the wider chip industry outside of two-dimensional materials entirely. The explosive demand for AI accelerators from companies like NVIDIA and AMD has pushed high bandwidth memory, produced by SK Hynix, Samsung, and Micron, into tightly stacked configurations, sitting directly next to compute logic. Because moving data short distances in 3 dimensions is far more energy efficient than moving it across a flat 2-dimensional board. If low-temperature, two-dimensional materials can eventually be layered into these stacks without damaging the silicon underneath, they would fit naturally into a manufacturing trend the industry is already committed to, rather than requiring an entirely new paradigm to be adopted from scratch. There is also a second, quieter application, ultra-low power edge devices. A smart sensor monitoring temperature, vibration, or environmental data does not need billions of transistors or gigahertz clock speeds. It needs a small amount of reliable, low-power computation close to where data is collected. A slow, atomically thin processor that sips power might actually be a good fit there, long before it is fast enough for anything else. Global competition. There's also a geopolitical layer worth understanding. The researchers deliberately chose the RISC-V instruction set architecture instead of designing something proprietary. RISC-V is open source, unlike ARM or x86, which require licensing fees. In legal agreements with a single controlling company, RISC-V can be implemented by any team, anywhere, without paying royalties to a foreign entity. That matters enormously in the current climate, where the United States has restricted Chinese access to advanced chip-making tools from companies like ASML, and where export controls on ARM-based designs and NVIDIA's most advanced AI accelerators have pushed Chinese researchers and companies toward architectures they can build and modify freely. China has been investing heavily in RISC-V across its semiconductor ecosystem, from Alibaba's chip division to smaller startups, precisely because it offers a path around licensing dependencies. Choosing RISC-V for RV32UGI was not just a convenient technical decision. It reflects a broader strategic pattern of Chinese research institutions, building on open architectures they fully control, insulated from the risk of a foreign supplier, cutting off access. This fits inside a much larger story about chip self-sufficiency that has been unfolding in China for several years now. Companies like SMIC have been pushed to develop advanced silicon manufacturing processes without access to the newest extreme ultraviolet lithography tools, because export restrictions from the United States and the Netherlands have blocked ASML from selling its most advanced machines into China. Huawei has been developing its own chip design and packaging workarounds under similar pressure. Against that backdrop, a domestically developed alternative semiconductor material built on an open architecture, running on Chinese fabrication equipment, and published for the world to see in a top-tier journal carries symbolic weight well beyond its technical specifications. It signals that Chinese research institutions are not only responding to restrictions on existing silicon technology, they are also actively hedging by exploring entirely different materials pathways that no export control regime currently governs. It's worth being clear about what this project does not prove. It does not prove China has leapfrogged Taiwan's semiconductor manufacturing company Samsung or Intel in advanced chip manufacturing. Those companies are shipping chips with billions of transistors at sub-2 nanometer nodes, produced at massive industrial scale with extreme ultraviolet lithography machines that took decades and hundreds of billions of dollars to develop. RV32WUGI, by comparison, was built using university laboratory equipment with transistor channels thousands of times larger than commercial silicon. This is not a substitute chip you could put in a phone tomorrow. What it does prove is narrower and, in some ways, more interesting. It proves that a team can take an alternative semiconductor material, one that has spent years as an interesting laboratory curiosity, and push it through the unglamorous, extremely difficult engineering work of building standardized logic cells, achieving high manufacturing yield, and assembling a functioning programmable system. That is a different kind of achievement than a faster transistor. It is closer to proving an entire manufacturing philosophy can work. Future outlook. Shanghai has reportedly announced plans for an engineering demonstration line intended to move this class of two-dimensional chip technology beyond individual university labs and toward pilot-scale production. That is a meaningful next step, but it is worth treating cautiously. Announcements about future demonstration lines are common in the semiconductor world, and the distance between a demonstration line and a commercially viable manufacturing process can span a decade or more. The things that still need to be solved are not small. Transistor channels need to shrink from 3 micrometers down toward dimensions competitive with modern silicon, which will require far more advanced lithography than a university lab currently has access to. Contact resistance between the metal wiring and the two-dimensional material needs to improve significantly, because right now some of that structural inefficiency is limiting speed and reliability. The process needs to scale from 4-inch research wafers to the 12-inch wafers used across the commercial industry, while maintaining uniform material quality across that much larger area. And critically, the field still needs a reliable path to complementary logic, meaning both N-type and P-type transistors working together the same way modern CMOS silicon does, because right now RV32.WUJI's design is limited to N-type devices only, using threshold voltage tricks as a workaround rather than a true complementary structure. Every one of these steps is a multi-year engineering program in its own right, not a quick fix. It is also worth mentioning that the industry already has a rough roadmap for what good enough looks like at this stage. The International Roadmap for Devices and Systems, an engineering framework used across the global semiconductor industry to track long-term technology targets, includes specific benchmarks for two-dimensional transistor performance. And independent analysts reviewing the RV32WUJI work have noted that Fudan's basic transistor structure lines up reasonably well with those 2022 roadmap targets. That does not mean the material is ready for commercial deployment. It means the fundamental transistor physics are landing in a range the industry considers plausible for future development, rather than falling short in some fundamental way. That distinction matters because plenty of promising lab materials over the decades have hit walls precisely at the physics level, not just the manufacturing level, and this appears not to be one of those cases so far. So where does this leave the future outlook for two-dimensional semiconductors more broadly? Realistically, silicon is not going anywhere for the foreseeable future. It remains, by an enormous margin, the most mature, best understood, and most cost-effective semiconductor technology ever developed, backed by trillions of dollars of accumulated manufacturing infrastructure. But the era of assuming silicon alone can keep shrinking forever is genuinely ending, and that is pushing serious global investment into alternatives. Companies and research groups around the world are exploring two-dimensional materials, gallium nitride, silicon carbide, and various stacked and hybrid architectures, each aimed at a different part of the problem, whether that is power efficiency, thermal management, or squeezing more logic into smaller and smaller volumes. What RV32 UGI adds to that landscape is a concrete existence proof, published under peer review in one of the most respected scientific journals in the world, that atomically thin semiconductors can be manufactured with enough consistency to build a real, working, programmable processor, not just an isolated transistor on a microscope slide. That single fact shifts the conversation. Researchers can now start optimizing yield curves, refining standard cell libraries, and improving contact engineering instead of spending years simply proving the basic concept can function at all. It also changes the kind of funding and collaboration this field is likely to attract next. Materials, science breakthroughs that stay confined to a single transistor on a microscope slide tend to attract academic interest and modest grant funding. A published, peer-reviewed, functioning 32-bit processor, even a slow and physically large one, is the kind of result that tends to attract serious industrial partners, government funding programs, and follow-on research groups racing to replicate and extend the result. Expect to see competing teams, both inside China and at universities in the United States, Europe, and South Korea, attempt their own two-dimensional processor demonstrations over the next few years, each pushing transistor counts, clock speeds, or channel dimensions a little further than Fudan's first attempt. Conclusion, plus CTESO. Here's my take. The 3-atom headline is the flashy part, but the number that actually matters is 5,900. Engineers have been building individual two-dimensional transistors in labs for well over a decade. The genuinely hard problem was never making one transistor switch cleanly. It was making thousands of them behave predictably enough at high enough yield to form a coherent system. Fudan's team crossed that threshold, and the way they crossed it, combining materials, science, circuit design, standard cell libraries, and machine learning-assisted process optimization, is a more meaningful signal than the raw transistor count. This chip will never power your next phone. It was never built to. Its job was to prove that the enormous engineering gap between an experimental laboratory transistor and a functioning programmable computing architecture can actually be closed. And on that specific, narrower question, the evidence published in Nature says yes, it can. Every semiconductor technology that has ever mattered started out looking uncompetitive next to the mature incumbent it eventually challenged, or more often, complemented. Silicon has had over half a century of investment, infrastructure, and refinement behind it. Two-dimensional semiconductors are only now beginning to build that same foundation, one working prototype at a time. So, what do you think? Will atomically thin materials like molybdenum disulfide eventually become a serious partner to silicon in future chips, handling sensing and edge computation while silicon keeps the heavy lifting? Or will this stay a fascinating academic detour that never leaves the lab? Drop your take in the comments, and if you want more grounded, fact-checked coverage of chips, semiconductor materials, and the technology race shaping the next decade of computing, subscribe to the channel and turn on notifications so you don't miss the next deep dive breakdown. Thanks for watching all the way through, and I will see you in the very next one on the channel.